Hi, in this video I'll be showing how to integrate secant to the fifth two different ways, one integration by parts and one by substitution. A little reminder, I'll start with integration by parts, and this is just a quick reminder of the formula. The integral of u dv is equal to uv minus integral of v du. I will not go into derivation of this, the background. I'll assume you've worked with this a bit and already understand the basics, but we'll just show an application of it here. We also need a few other tools to use, and again with these basics I will not be going through why they're true or the derivation. We'll just assume that you know them or just can accept them as true. We have to start somewhere in a limited video. So the integral of secant squared is tangent. I'm not going to go through that why here or how you can derive that. Just you can figure that out by the derivative of tangent being secant squared, for example. The integral of secant is the natural log of secant plus tangent. Again, I'm not going to go through that. We'll just accept that as a basic here. You can look that up somewhere else for now. And trig identity tangent squared is equal to secant squared minus 1, which we'll use. So these are my assumed basics and the integration by parts formula and later substitution formula. So when you're using integration by parts, it's kind of nice to pick a dv that's easy to integrate. Otherwise, the whole point of integration by parts is try and simplify the problem so you can solve it analytically using this trick. And then you want to pick a dv that's easy to integrate. Otherwise, you haven't really simplified your problem so much. So in this case, we'll pick dv equal to secant squared dx. And that allows us to use, maybe I can get the laser pointer here. That allows us to use this identity here that I said we're going to assume. Since we know the integral of secant squared is tangent, then this becomes easy to integrate. So we go through integration by parts here. So if dv is going to be secant squared, then that leaves 3 secants left, so secant cubed. So we let u equal secant cubed x. And then du is just the derivative of that, which is going to be 3 secant squared x, secant x, tangent x. So that's just simple derivative of secant cubed. Which we can simplify a little bit to 3 secant cubed x tangent x dx. So this is our du term here. And it's simply the derivative of this, which we assume because we decided we're going to take dv to be secant squared. And then, as we saw on the previous page, the integral of secant squared is tangent, so v becomes simply tangent x. And in general, taking derivative is easier than integrating, so that was one of the things that motivated our choice. Sometimes you want to choose your integration by parts so that the derivative makes the problem easier, but in all cases, it's important that your integral, your dv, is something that's easy to integrate. If your dv is harder to integrate than your original problem, or as hard, then you haven't really gained anything. So, using the integration by parts formula, then we can rewrite our integral here, integral secant to the fifth, as uv. So here we have u times v minus the integral of v du. And this is our du here. So this is uv times minus the integral of v du. So we just applied the integration by parts formula now. And here we can do a few simplification steps. We haven't touched this term yet, which we can leave because that one's basically done. But we can combine the two tangents here into a tangent squared, and this 3 we can take outside the integral sign. So the next step is to remember this formula we talked about in the beginning, that tangent squared can be replaced by secant squared minus 1, and that allows us to not have different trig terms here, then everything becomes in terms of secant. So we're now going to replace tangent squared with secant squared minus 1. So again, the UV term is the same, 3 is the same, secant cubed is the same, and now all we've done is replaced tangent squared with secant squared minus 1, according to this trig identity. Now we can distribute out this secant cubed here between these terms. So we've done that here. We haven't changed this. This is the same, and all we've done here is multiply through with the secant cubed through the parentheses. And then I break up this. This is one integral here, so I'm going to break into two separate integrals, right? Because we can do that. So this is minus 3 times this integral, and then minus 3 times, and this is a minus sign, so it becomes a plus 3 times the integral secant cubed. So at first sight, we've not gained anything because this term in red here, we see a secant to the 5th. And we start with secant to the 5th. So it feels, at first it can feel like you've gone in a big circle. It feels unproductive, you know, that we haven't made the problem simpler since we've ended up back where we started with just a bunch of extra terms. But actually it's not entirely true. Because we have 3 of them here and 1 here, so we can actually treat this algebraically. So if to simplify this, we could just call the integral we want, the integral of this, we could just call it I, right? We could just write some random letter here. Everyone likes I because I stands for integral, so we just write I equals, right? And we're just saying I is the integral we're looking for. I is equal to the integral secant to the 5th. Okay. But we have I here, but then we have 3 i's here. So it's like an algebra equation, right? So we can rewrite that. I wonder if I think I have that rewritten in the next line. So we add the I here, we rewrite it, and then this is also I, right? This part in red here is also I. Same thing. And we have 3 of them. So we just, all I've done is substituted I for secant to the 5th, and then we have minus 3i here. And now we can bring this, like a normal algebra equation, over to the left side and then divide out, and then we've gotten rid of our new secant to the 5th. So I've just copied that last line up to the top here where we were, where we just I and substituted in for 3i, the integral we're looking for. And so if we bring this over to the left side, we have 4i is equal to these other terms that we have now. So we can just divide through by 4. And we get I is equal to 1/4 of this expression plus 3/4 of this integral. And now you can see that we have a new integral we have to deal with, secant to the 3rd, but that's simpler than secant to the 5th. We've lowered the power of secant. So we didn't go in circles we see now. We didn't get it more complicated. We've actually lowered the exponent of our secant. We have more work to do, but this is a step in the right direction. We have simplified the problem because this I now is what we're looking for. So it wasn't a problem that extra secant to the 5th showed up in our solution. So just substituting this back into I, we see this is what we're looking for, and we see it's equal to this term plus 3/4 of the integral secant cubed. So now, of course, we have to figure out the integral of secant cubed. So we're going to do that separately and then come back and put that result into this equation to get the final result for our integral. So we'll treat this as a completely new integral, the integral of secant cubed. And we'll treat it in the exact same way we treated secant to the 5th. And in that case, we should get one more step, right? If we think of it works about the same way, then we should be able to reduce the exponent twice again. Right, that would be our expectation. We went through this step with the integration by parts. We reduced the odd exponent by 2 steps. Became from the 5th to the 3rd power. So then we should, if we did a similar thing with secant cubed, maybe we expect that it'll reduce it by 2 steps. We ended up with secant. But if you remember, the integral of secant was one of our assumed tools so that we have an answer for it directly. So we assume that that's maybe going to happen, and we try that, and we'll see that it is actually what will happen. So we start a whole new problem here, integral secant to the cube, and we do this exactly the same way, integration by parts. And again, we pick dv to be secant squared because it was easy to integrate, and that leaves us only with secant left. And we take du of secant, which is this expression here, which is the normal derivative of a trig function. Use the integration by parts formula again. uv minus the integral of v du. No problem. And just like we did before, now we're just repeating what we did before. We combine the tangent term to get tangent squared. This is identical to what we did before. We use the tangent squared identity to change everything into secant. Here we just substitute in tangent squared, exact same thing we did before. And now we multiply out the secant through the parentheses, exactly like we did before. And then we separate this integral again, like we did before. So it's this minus sign distributes through here. So we have this becomes a plus, the integral of this. Last time we had a 3 here. We don't have that extra term now. And once again, we see we have our integral repeated. Last time we had it with secant to the 5th, we had a 3 in front of it, so it became 4 on the other side. We're going to do the same trick again. We're going to have I equals, but here this is a minus 1, so we're going to have 2 on the left side instead. So it's not a problem that we saw, as we saw before, that we ended up with a secant to the 3rd again, just like it wasn't a problem we ended up with secant to the 5th last time. So we're going to do the same thing. We're going to write this in terms of I. Then we see that this is also I, but it's minus I, and then we're going to move it over. We'll just do a little algebra. So we rewrite this in terms of I, and we see we can change this to I as well. It's the same thing. And I'm just bringing it up to the top here again, what we had in the last slide. And all I do is I move this I over to the left side, normal algebra. Then we have 2I on the left side. And now I can divide by 2 to get I by itself. And of course, I is the actual the integral we're looking for. So I can resubstitute it back in. And also remember this identity, this integral I gave you at the beginning is one of our assumed integrals, which I will not be going through. The integral of secant itself, and that's the natural log of secant plus tangent. And you can either look that up. I don't know if I'll do a video on that one itself. So changing I back to secant cubed, because that's what we're interested in. That's what I was equal to. We see that the integral of secant cubed, and putting this in for secant is equal to 1/2 secant x tangent x plus 1/2 the natural log of the absolute value of secant x plus tangent x. Of course, plus c, but we're just going to put that in at the total value at the end. Because we wanted this to add into our integral we wanted this to add into an integral of secant to the 5th. So now we've done a little side step here to figure out secant cubed, so we can add this value back in, all the way back into our original result. So this, to remind you, was the original result we got, and then we took a side step to figure out secant cubed, which we got this result. And so now we have to put all of this into here and not forget the 3/4. You got to be careful of these terms here. Let's multiply through, which gives us this really horribly long, messy expression. And here we've added our plus a constant now at the end to be correct. So this is the integral of secant to the 5th. And that was how we can do it, by integration by parts. A lot of steps. You could, with other powers of secant, higher powers of secant, you could do with any odd powers of secant would work in exactly the same. You'd reduce it by 2 every step until you ended up with the integral of secant itself. They would get progressively longer and messier, of course, the result. So as promised, I will show you another way to do this using substitution. So here we're going to do a classic U substitution. So when you do U substitution, you need to think a bit about your du. This is important. So you can ask yourself, can I find or create du in some way that makes the integral easier? Because that's the whole point of substitution, is you want to make the integral easier. You don't want to just randomly substitute in. You want to find something that's going to make it easier. And then the du itself is a big part of that. So is there a nice du there? If there's not a nice du already there, can you create it? Can you do some clever algebra that creates a nice du? So can you add it in for somehow with inverse substitution? Will it make things harder or easier, right? Because sometimes you can create a du with inverse substitutions and suddenly everything gets really ugly and you didn't actually make your problem easier at all. It instead got a lot harder. And that's a little bit about getting the feeling for calculus and when this works. And it's You can talk about things to look out for, but a little bit is like practicing and just getting a feeling for this. So the whole point of using substitution, the basic idea is you want to make the integral easier to solve. Otherwise, there's no point in doing it. So we're going to start by rewriting, in this case, secant as cosine. And we remember that secant is 1 over cosine. So our integral of secant to the fifth is the same thing as integral of 1 over cosine to the fifth. So looking at this, it looks like, well, it'd be really nice if we could just use u equals cosine x, because that would be a nice substitution, and that would be rather easy to solve by normal integration techniques. But we can't quite do that because we have a du problem, right? And the du in this case is minus sine x dx. So that we don't have a minus sine x dx there. So that doesn't help us right now. But maybe it can lead us in the right way of thinking, right? We need like a trig function on top. So this isn't possible at first glance, but it can help us lead us in the right direction, right? So maybe we can create it. So we can be a little bit creative and remember our basic identity of sine squared plus cosine squared equals 1. So that means that any even power of cosine can be turned into sine, and any even power of sine can be turned into cosine. So that's nice to remember. We have an odd power of cosine, so that's a clue there. So if we had an even power, we could turn into sine, and we need a cosine or sine dx if we want to take the derivative. So putting this together, being a little creative, maybe we can the idea that I'm going to use here is we multiply by cosine over cosine, right? Which is just multiplying by 1. Doesn't change anything. And that gives us an even power. It gives us a cosine in the numerator, and it gives us an even power of cosine in the denominator. And an even power of cosine we can change into sine, which means we have sine in the denominator and cosine in the numerator, which is the derivative of sine, and suddenly we have our du. Voila. So this little trick here, it gives us cosine on top and an even power on the bottom, and we see, hey, now we can change this to sine, and cosine x dx is the du if we have a derivative of sine. And now this leads us in the right direction for substitution. And so we do that by changing the cosine, the even power, to sine. So first we change it to cosine squared up to some power. So that's cosine squared to the third power in this case. And then we change our cosine squared to 1 minus sine squared. So now we have sine in the denominator only. And now we have our way forward for a substitution. And I just copy that last slide over here. And so now we can use u is equal to sine x because we've created du in the integral now. So u is sine x, du is cosine x dx, and there's our wonderful du just sitting there that we added in. And all we have is sine aside from the du, so we're doing really well there. So we can change this trig integral to a polynomial integral instead. Or a rational polynomial, a rational function anyway. But still easier than the trig integral, depending what you like. We could solve this in different ways, but one way to do it is by using the method of partial fractions. So we'll now use partial fractions. First note that 1 minus u squared, of course, is 1 plus u times 1 minus u. So we rewrite that first as the two base factors there. So it's 1 plus u to the third times 1 minus u to the third. And then we use the technique of partial fractions. And I'm not going to go over why. I assume that you've worked with partial fractions again before doing this. If not, you need to review partial fractions, but you would set it up. You have to take into account the powers. When you have repeated powers of a factor, you have to take into account successive powers of the factor. So we have a bunch of equations to solve here, but it's a straightforward algebra. A little messy perhaps, but not too bad. So multiplying everything out, we see that this horrible, messy polynomial here is equal to 1, but even though we have 6 variables, we actually compare coefficients of the different powers of u, so it's not that bad. It's just a lot of algebra. I'm going to go through it a bit briefly. I'll let you work through it. The algebra itself is straightforward, though a bit messy. So I'm going to go through it a bit quickly, but I'm not going to go through all the details. But all you're doing is comparing the coefficients. But we can do one simplification first. So this was our big messy equation. And you note that the coefficient of all powers of u will be 0, right? Because on the right-hand side, we only have a constant. So all the coefficients, all the powers of u will be 0. So we have, if we look at the u to the 5th term, where do we get u to the 5th? We're going to get a u to the 5th here, right? And here we'll only have u to the 4th, u to the 3rd, u to the 5th here as well, u to the 4th and u to the 3rd. So these are the only 2 terms that are going to have a u to the 5th at all. And if we look at those terms, right, this is going to be u squared minus u cubed times the negative u cubed, which will be negative u to the 5th times a. That's this term. And here we're going to have u squared, because even though it's minus, it's squared, so it becomes plus u cubed. So that's u to the 5th d, and that's going to, these coefficients together are going to be 0. So minus a plus d equals 0, so we get a equals d. So that's an easy first step here to determine that a equals d. And then we can combine the a and d terms and simplify. Right, so I just changed, I rewrite this as what did I do here? So this is, change this to an a, and 1 minus u squared, 1 minus u squared. I see, I took 2 of these out. All right, I wrote this a long time ago, and I feel very unprepared suddenly talking about this, but I'll let you work through the details here. So this was a simplification you could do pretty quickly, so I will just let you follow through the details later and not take time to remember all the steps I did here to simplify. But anyway, putting that back in, that's one simplification here. As I said, I'm not going to go through all the details of the algebra. I don't want to make this video any longer than it already is, which is probably too long. And there's still a lot of algebra to do here. So it's not necessarily easier to do the partial fractions, but it depends how much you like the algebra. Multiplying it out, you get this. Multiplying that out, you get that. So this is just all the things multiplying out the algebra. You can check this later, do it yourself. And this is rewriting it, and I've color-coded now the terms with the same powers. So you can see all the u squared terms are in blue, all the u to the 4th terms are in purple, all the u terms are in red and the constant terms are in black to make it easier to combine. So you can do this to check your work later. And of course, you get the different coefficients here. And this is something I do. I write u to 0 with the constant term, so it's very easy for me when I'm doing my notation. I take all the powers, write u to the fourth, u to the third, u to the second, u to the first, u to 0, to have a consistent and easy notation for which of the variables I'm doing. And of course, all the coefficients of the u terms are 0, as we said before, and all the constant terms have to add up to 1. So this is a system of equations you need to solve with basic linear algebra. So if you do the steps and solve the system of equations, this is what I get in any case. And I think I checked it, so I'm pretty sure it's correct. Just basic algebra. Right, so then we put in all our coefficients now that we solve for the partial fractions, and we get this huge messy thing here. But now each one of those is fairly easy to integrate each term there. So this is the integral after you integrate. This is what you get after you integrate each term. With standard integration techniques, these are all quite simple integrals, each one. We'd rather not have 6 terms here, so we can look to see if we can combine them in some smart way. And luckily, yeah, we can actually do some combinations here and do a little smart thing with common denominators and put the log terms together. So doing that work of simplification, this is the first step where we put the log terms together. We found a common denominator for the fraction terms, the rational terms, and we could do a little bit more simplification there, and then even more simplification, and we end up finally with this expression here after a lot of algebra and a lot of simplification. And of course, if you remember, our u is sine x, so all we do is put back in our sine x now to get back to our original in the x world, as they say. We were working in the u world, we go back to the x world. And so all we do is substitute back in sine x. And then right, I just simplified a little bit here. 1 minus sine squared, I wrote as cosine squared. This is a question of taste. What form you want to write it in is up to you. I thought it was a little simpler to change the 1 minus sine squared to cosine squared. It was just a little less, fewer terms there. But like I said, this is a matter of taste. So you could leave it like this if you like. I put it into this form, and don't forget your constant at the end. So this is using substitution, the integral of secant to the 5th. Messy algebra, but otherwise straightforward. You might be noticed that these the results look extremely different, right? How do you know that? I mean, are these actually the same? And you can test this in different ways. An easy way is you could type in these expressions on Wolfram Alpha and see that they're a constant, or differ by constant. In this case, it might even be exact, differ by 0. But if you could take one expression minus the other expression, for example, and try and graph it, and it should be a straight line, right? If they're the same, because it's possible that they differ by a constant. So you could get some other constant besides 0. So you can check that these expressions actually are equivalent. You could also try and integrate both expressions and hopefully end up with secant to the 5th, but the problem is I think that's quite messy and a lot of work. So I find it easy way to check is just type them into Wolfram Alpha and subtract one from the other and graph them to verify. And this is something to keep in mind with trig integrals. There are a lot of different solutions often that are equivalent, even if they don't always seem that way. Which is also why it's very important to show your work in school. So I hope that was helpful.